All right, buckle up, everybody, because today we are diving headfirst into the weird and wonderful world of the periodic table.
That's right. Get ready for a deep dive.
And you guys know how much I love a good deep dive, especially when it comes to topics you requested.
Absolutely.
So we're not just, skimming the surface here.
Yeah.
We're going to unearth the hidden stories, the aha moments, the things that make you see the periodic table in a whole new light.
Exactly.
And our trusty guide for this journey, Wikipedia's own article on the periodic table. We're talking predicting elements before they were even a thing, helium's little identity crisis, even a sneak peek at the future of the table itself. Get ready, it's going to be wild.
It's going to be a wild ride.
So let's start with the basics, but trust me, we'll be twisting those basics pretty quickly. Everyone remembers the periodic table from school, right? That big, colorful chart on the wall. But have you ever stopped to think, why is it organized that way? What's the method to the madness?
It's like the universe decided to organize its building blocks.
Exactly. And each element, it's got its own little ID card, starting with its atomic number.
Yeah.
Now, I know, atomic number sounds kind of basic, but it's more than just a number,
Yeah,
right?
absolutely. It's fundamental.
Like an element's fingerprint,
Exact.
telling you
Fundamental.
exactly how many protons are hanging out in its nucleus.
And that one number dictates so much about how that element behaves.
It's wild, this tiny little thing determining an element's whole personality. But wait, it gets even cooler, because then you've got these things called isotopes,
Right. Isotopes.
which are like different versions of the same element. Like imagine having different editions of the same book.
Yeah, that's a great way to put it.
They've got the same atomic number, so the same number of protons, but the number of neutrons is different.
Which can actually affect their properties,
Yeah.
sometimes in really interesting ways.
Okay, so we've got these isotopes, these atomic fingerprints. But then we get to electron shells, and that's where my brain starts to go a bit like, whoa. It's like those Russian nesting dolls.
I see where you're going with that.
Each shell is like a level,
An energy level, yeah.
and the electrons are trying to find their spot.
Exactly. Electrons want to be in the lowest energy level possible, as close to the nucleus as they can get.
So it's not just a random free-for-all. These electrons have got rules, right?
Yes.
They're organized.
Very much so.
And that organization, that's what we call electron configuration.
And that's the real key to understanding the periodic table.
Okay, so let's unpack that a bit, because I feel like electron configuration is a pretty big deal here.
Oh, it's huge. Basically, elements in the same vertical column, what we call a group, they have similar chemical properties because they have the same number of electrons in their outermost shell.
Ah, okay, so it's all about that outermost shell. That's where the action happens.
Exactly. Think of it like this. Those outermost electrons, they're the ones interacting with other atoms, forming bonds, causing reactions. It's all about those outer electrons.
So the periodic table, it's like this giant map of electrons' social lives.
You could say that. It's all about how those outermost electrons are arranged and how they interact.
Mind blow.
It's pretty incredible, right?
And that, my friends, is how we go from tiny little electrons to the entire organization of the universe.
And we're just getting started.
It's amazing how these tiny little particles, these electrons, can have such a huge impact on, well, everything.
It really is the essence of chemistry, isn't it?
And speaking of chemistry, this electron configuration business, it's not just about understanding how elements behave today, right? It actually played a huge role in one of the most, audacious predictions in science history.
Oh, absolutely. We're talking about Dmitry Mendeleev
Yeah.
and the creation of the periodic table itself.
Right. Mendeleev, the OG of element organization.
He was a visionary, that's for sure.
So paint the picture for me. It's like the 1860s, right? And we're just starting to understand what atoms even are.
Right. It was a very different time for chemistry.
And Mendeleev, he's like, I'm going to organize all these elements. But how? Where do you even begin?
Well, at the time, most people were just focused on atomic weight, but Mendeleev, he saw something more.
He was like, there's a pattern here.
Exactly. He realized that if he arranged the elements by atomic weight,
Yeah.
but also considered their properties, there were these repeating patterns.
Okay, so he's creating this table, this grand scheme of elements, but I'm guessing it wasn't all there yet, right?
That's the amazing part. He left gaps.
Gaps. He just left blank spaces.
He did. He was so confident in the patterns he saw that he said, nope, there's something missing here. We haven't discovered it yet, but it should exist.
That's some serious confidence in your work right there.
And get this, he didn't just say, oh, there's an element missing here. He predicted what those missing elements would be like.
Oh, he predicted their properties.
He did. Their atomic weight, their melting point, even how they would react with other elements. He even gave them placeholder names,
Oh, wow. Like what?
like Eka aluminum, for example.
Ecoaluminum. Sounds kind of futuristic.
It does, doesn't it?
Yeah.
But years later, guess what?
They discovered it.
They did. They found gallium, and it matched Mendeleev's predictions almost perfectly.
That's incredible. It's like he had a time-traveling chemistry textbook or something.
It's a true testament to the power of understanding those underlying patterns, those electron configurations.
So Mendeleev basically predicted the future of chemistry, all thanks to this idea of electron configuration.
He laid the groundwork for our understanding of the elements as we know it today.
But speaking of the periodic table as we know it today, there's always that one element that seems a little out of place. Am I right?
You're probably thinking of helium, aren't you?
Helium. It's always felt like the odd one out.
It does seem that way, doesn't it? Especially when you consider those electron configurations we were talking about.
Because it's in with the noble gases, right? The ones that are all like, nope, we're good. We don't need to bond with anyone.
Exactly. Group 18, the loners of the periodic table.
But helium, doesn't it only have 2 electrons in its outer shell?
You're right, it does.
And all the other noble gases have 8, right? A full outer shell.
You've got a good memory.
So helium's like an honorary member of the cool kids club, even though it doesn't quite fit the dress code.
That's a fun way to put it. It all comes down to its behavior.
Ah, so it acts like a noble gas, even though its electron configuration is a bit different.
Exactly. Sometimes those chemical properties trump the strict electron rules.
The periodic table, where the cool kids and the rule breakers hang out.
Where we get to unravel those mysteries and see how it all fits together.
It's like trying to put helium in a box with the other noble gases. And it's like, hey, I'm here for the party. But it's brought its own snacks, and it's just doing its own thing.
Helium marches to the beat of its own drum, that's for sure.
And that's what I love about the periodic table, honestly. You think you've got it figured out, and then bam, helium throws a curveball.
It's always got a few surprises up its sleeve.
But speaking of surprises, there's this whole other end of the periodic table we haven't even touched on yet. The super heavy elements, the ones that sound like they belong in a sci-fi movie.
Ah, yes. Those are the real heavyweights of the periodic table.
And we're talking elements that don't just occur naturally, right? We're talking about scientists creating them.
We are. It's the ultimate chemistry experiment, smashing atoms together to create something entirely new.
So how does that even work? Are we talking like giant microscopes and tweezers? How do you even make an element?
Think bigger. We're talking massive machines called particle accelerators.
Okay, now we're talking.
These things are incredible. They use powerful magnetic fields to accelerate particles to nearly the speed of light and then smash them together.
So it's like atomic billiards, but way more intense.
Exactly. And if those collisions are just right, boom, you've got yourself a new element.
That is so cool. But then how do you even know what you've created and where does it fit on the periodic table? Do you just get to pick a spot?
Well, it's not quite that simple. This is where our understanding of electron configurations really comes in handy.
So even with these brand new super heavy elements, it still comes down to those tiny little electrons.
You got it. By studying the way these new elements behave, we can start to figure out how their electrons are arranged.
And that tells you where they belong on the table.
Precisely. It's like solving a puzzle, but instead of pieces, we're dealing with subatomic particles.
That's incredible. But I have to ask, it can't always be that straightforward, can it?
You're right. It gets even more complicated as we get to those heavier and heavier elements.
Complicated how?
Well, those familiar patterns, those trends that work so well in the main part of the table, they don't always hold up so well down there.
What do you mean?
Think about it. These super heavy elements, they have so many protons and neutrons in their nuclei. The forces at play are immense.
Okay, that makes sense.
And those forces, they can actually start to affect the behavior of the electrons.
Wait, so the rules of physics are messing with the rules of chemistry?
In a way, yes. It's called relativistic effects, and it's a whole other layer of complexity in the world of super heavy elements.
So we're talking about elements so extreme, they're basically breaking the periodic table as we know it.
Not breaking it exactly. More like bending the rule.
Bending the rules, breaking the mold. These super heavy elements sound like my kind of party.
They're definitely shaking things up in the world of chemistry.
Well, there you have it, folks. From tiny electrons to giant particle accelerators, from predictable patterns to rule-breaking elements, the periodic table is a journey of discovery, and it seems like we're still just scratching the surface.
We are. And that's what makes it so fascinating. There's always more to learn, more to explore, and who knows what other surprises are waiting for us on the periodic table of the future.
I, for one, can't wait to find out. Thanks for joining us for this incredible deep dive into the heart of chemistry. I'm your host, signing off and reminding you to always keep asking those curious questions.